initial temperature equals negative mass of the water, which is 100, times specific heat, which was 4.184, times T final water minus 20.
This should be pretty much what I had on the other page, except for I put in the initial temperatures.
So questions about where this comes from?
All right, this might look kind of like a mess. Let's see if we can clean it up a little bit.
First off, what is 73.39 times 0.9?
6.651.
6.651? Can't be 6.65, I must have misheard.
Oh, no.
66.
Yep.
0.051. 66.
It was 051.
0.051 times, all right, so I'm just gonna, the final temperature is the same for the aluminum and the water, so I'm just gonna put big T minus 100 equals, that one I can do, negative 418.4 times T minus 20. Now I'm gonna distribute. Whenever I got a number sitting or anything sitting right outside what's called a binomial, something in parentheses where I'm adding or subtracting, I got two things there, that's bi and binomial. I multiply this times each, so I got 66.051 T minus 100 times that, so 6605.1 equals, now I multiply this, negative 418.4 T plus, because I got a negative times a negative. So that is going to be 8368.
Yep.
Now I need to get the T's together and the things without T's. So I'm just gonna get this over to here and this over to here. In order to go across the equal sign, I gotta do the opposite. Since I've got a negative here, I'm gonna add. So I'm gonna add 418.4 T. And then I need to get this over to the other side. Since I'm subtracting it, I need to add it, plus 0.6605.1, plus 0.6605.1. Those cancel out, which is the whole reason I did that. And these add up to something spectacular. So 45T period, 4 carry the 1, 8. You got 484.45 T. I think I saw one knot. And then over here, 0.1, so 8, 5 is 13, carry the 1, 7. 9.4.
Yep.
Okay. And now I need to get T all by itself. Well, I have to get rid of that 44.45, and since it's multiplied into T, I gotta undo that. Division takes care of the multiplication. If I do it to one side, the math people say I gotta do it to the other. So my final temperature, after all of that,
30.91.
let's finish it off.
Celsius, degrees Celsius.
You didn't sound particularly confident with that degree Celsius.
Degrees Celsius.
Yeah, there we go. I know, you're looking at that and going, oh man, I'm glad I was here. I feel so much better as a human being.
Any questions before we talk about, does this answer make sense?
So that's the degree that the aluminum block is.
That is the,
Are
that's the temperature, the water will warm up to that temperature and the aluminum block will cool down to that temperature.
Okay, so they're both equally
Yes,
that temperature
yeah.
at the end.
When, at this point right here, when I said that the final temperature for the aluminum and final temperature
Yeah.
of the water were the same, that's
Okay.
sealed it. Jennifer, so you were looking like you were double checking something. Everything good?
Yep.
All right. Okay, so let's see if this makes any sense at all. I've got aluminum, I've got water. They're not exactly the same mass, but they're kind of at least the same ballpark. I mean, I've got 73 and 100 grams. Let's look at the rate at which they lose energy or gain. They change temperature. I've got that compared to that. Just make sure I'm in the same unit system there. I am. Hewitt, I think, makes reference to this specific heat as sort of a thermal inertia. The higher the number is, the harder it is to change the temperature. Because this takes 4.184 joules of energy to change a gram of water, to increase a gram of water 1 degree Celsius. This only takes 0.9 joules to do the same thing for aluminum.
You said the higher the number it is, it's harder to change
The temperature.
temperature.
The more
More energy it takes.
more energy it takes to do it. So I have an aluminum block here and water. Since the water has a much higher specific heat, more thermal inertia, I do not expect the temperature of the water to change as much as that for the aluminum. And in the end, the water changed about 10 degrees Celsius, and the aluminum changed about 70 degrees Celsius. So that matches what I would expect. Why should this be here? All right, see if I'm guessing correctly what you're thinking. You're thinking, man, that was so cool. But suppose we didn't know the specific heat. Is there a way to calculate it?
Probably.
Good. I've seen a couple nods. Looks like I nailed that one. All right, I need to erase some stuff. We can keep all of that the same. Well, actually, the only thing that's gonna change in this problem here is on this page, or the previous one, so let's go back to, back on another one. Still the same setup. I got an aluminum block. I have some metal block, which we know is gonna be aluminum. I don't have to find the mass using the density. I could just take a triple beam balance and stick it on there and see what the mass is. I could identify the mass, the material based upon the density, or at least narrow it down. But let's assume that it's the same block, so we know the mass of it. I know that the energy change, the heat exchange from the, I'll just do M for metal, plus that for the water is equal to 0. We're gonna pretend we don't really know it's aluminum. This becomes mass of the metal times specific heat of the metal times the change in temperature of the metal is equal to and bringing that over, negative mass of the water, specific heat of the water, change in temperature of the water. So in essence, what we did, we took this metal block, put it in boiling water for a few minutes, transferred it very quickly over into the other water, covered it up so that heat won't escape, and then we measured the temperature of the water just to see what it gets up to. So let's say that the water gets up to, I don't know, let's say 30 degrees Celsius. So this time I know the final temperature is 30 degrees Celsius. That's just a different unknown. I know the mass of my block, so that's 73.39 times the specific heat of it, times the change in temperature. Well, it ended at 30 degrees Celsius, minus 100 degrees Celsius. Because I'm putting units in, I should do it all the way across the board. And that's going to be equal to negative mass of the water times specific heat of water. You know, let's do the other unit system. Let's do 1 calorie per gram degrees Celsius times the change temperature. It ends at 30 degrees Celsius and it started at 20. The units of my specific heat are basically dictated by the units I used over here. So the math problem, 73.39 times negative 70 times the specific heat is equal to, well, that's 10 equals negative 1,000. Someone could tell me what that is?
Negative 5,137.3.
Negative 5,173.3.
37.3.
The negatives, I have one on both sides, so I have 5137.3 times Cm equals 1,000. So Cm, bringing this over. And I get somewhere just shy of 0.2.
Isn't 1,000 negative? Or,
I have a negative here and a negative here, and the negatives would cancel.
okay.
I got 219465. Do we cut it off?
Give me units at this point. Is it centimeters? No. It's not going to be a single word.
We were solving for CM. We were solving for CM, right?
Yes. Let's just take a quick gander at units here. So I'm looking at this equation right here, and I'm just going to look at the units. So I have grams times whatever the units of Cm are, times degrees Celsius, equals, and then over there I've got grams times calories per gram degrees Celsius, times degrees Celsius. Anything cancel out?
The grams and the degrees Celsius. Like one and, yeah,
Are those the ones you wanted to cancel out?
yeah.
Okay.
So would it be Kelvin for G degrees Celsius?
Yeah. I need to isolate this, so I bring the G over, the delta, and the, not delta, degrees Celsius over. For those who are old school. Centigrade. So it's gonna be calories per gram degrees Celsius. If it were aluminum, I would expect 0.215. But I got a little bit less because, well, I rounded down for the temperature. I rounded down to 30 degrees Celsius, which meant that the block lost more energy, so the specific heat was smaller. It matches.
So the 0.194 was the amount of energy that was lost, or not lost, but
That is the amount of energy needed. If it's gonna lose temperature, that's the amount of energy that needs to be lost to change 1 gram of the substance 1 degree Celsius.
okay.
If it's gaining temperature, that's the amount of energy I need to put in order to do that. Questions on this? All right, why don't we take 5, we're gonna come back, we're gonna see how much energy it takes in order to take an ice cube and bring it up into, turn it into steam. And then we'll talk about the laws of thermodynamics. Starting from the 0th to the 3rd. Enough video of nothingness. All right, let's do this. It's going to happen in 5 steps. We can't just use MC delta T. Why not? Why can't I just do Q equals MC delta T? So the mass is 200 grams. Change temperature is going to be 125 degrees Celsius. And C is what? Why am I not able to tell you C?
C's not the 2.089?
That is it for ice.
Oh, ice. Oh, solid. Okay. Because we don't have steam, or,
For
we don't have steam for the energy equation?
we have C for ice.
Steam. Steam, do we have C for steam?
We have C for steam. Yep.
Or
That's
is it
the
G?
third one,
Ah,
with G.
The G, 2.01.
Yep. I mean, you're hitting on the problem there. I have a specific heat for ice. I have it for liquid water. I have it for steam. But they are not all the same number. This formula assumes there's no change in phase. We have to somehow figure out how much energy it takes in order to change phase. In other words, we go from, we're starting out in solid. First we have to get it up to the melting point, and then we melt it. Then we have to get it up to the boiling point, and then we boil it. And then we get it up to our final temperature.
So before the aluminum wasn't changing,
Right.
okay, but now the ice is changing the steam, so you can.
Absolutely.
Okay.
So the first thing we're gonna do, so I know it will melt at 0 degrees Celsius, it will boil at 100 degrees Celsius. So the first thing I put energy into it to get it up to 0. Then I need to put energy into it in order to melt it. As it melts, it does not change temperature in our nice ideal situation. Then, once I've melted it, I have to raise the temperature again. Once I get it up to 100 degrees Celsius, I can now boil it. So I turn it into steam. Once I have it in steam, I can heat it up again. So I'm going to use something slightly different in each of these phases. There's a couple of forms, there's 2 formulas that I'm going to need. So the ones where I'm changing temperature, it stays, here it's ice, here it's liquid, here it's steam. I have a formula for those 3 phases, right? Those 3 parts right there. I can use this because I do have a value for C for ice, liquid, and gas. So let's do that, and then we'll talk about the phase changes. So I will label this 1, 2, 3, 4, and 5. So in section 1, I have ice, and my specific heat of ice is like 200 there, okay. Either one of these, so I guess we'll stick with joules. 0.9 joules per gram degree Celsius. 0.9 joules